A pyramid has height h and square base with side x. Here's its volume. If the height remains fixed and the side of the base is decreasing, at what rate is the volume of the pyramid decreasing when the height is 120 meters and the width is 150 meters? What? How could a pyramid be getting smaller? Erosion? Is that happening with Great Pyramids? Yeah. Though probably not necessarily as described here. A pyramid with a square base so this is supposed to be a three-dimensional picture. Has height h. Of course, erosion would erode the height as well, not just the base. So this is interesting. If you look this up, the Great Pyramids in Egypt used to be a lot prettier than they are now. They used to shine in the sun. Like they were covered in a shiny material like 1,000 years ago. And the base is x, and it is a square base, so it's x all the way around. The volume is 1/3 x squared h. That is the volume of such a pyramid. X squared h would be the volume of a box shape with base x and height h. It turns out when you make box shapes into pyramid shapes, you do need to multiply by 1/3. That happens with cones as well, where you take the area of a cylinder and the volume of cylinder and multiply by 1/3 to make a cone. Yeah, if the height remains fixed and the side of the base decreases by 0.002 meters per year. Let's see, that would be like 2 millimeters per year, I think. Did I convert it right? At what rate is the volume decreasing when the height is 120 meters and the width is 150 meters? So h is not changing. H is staying fixed, but x is changing. We're given that dx dt, the rate of change of the base length, is not 0.002, but negative 0.002, because it's decreasing meters per year. What do we want to find? The question says, at what rate is the volume decreasing? Find dv dt when the height is 120 meters and the width, which is x, is 150 meters. That's what we want to do. I said a couple minutes ago, this is kind of like implicit differentiation. Definitely not the exact same thing, but kind of has a similar feel. With implicit differentiation, we had an equation, say, involving x and y, and we wanted to use the equation to find dy dx. We assumed y was a function of x. Turns out that's a valid assumption near most points on the curve, at least near points where the tangent line is not vertical. Little pieces of the graph will pass the vertical line test, even if the entire graph doesn't. So it's a valid assumption under those circumstances. Here, we're not assuming x is a function of h or h is a function of x. We're assuming x and h are functions of t, time, although h is a constant function of time. But we could modify that assumption too. We could assume h decreases as well. It's just not what the problem says to do. maybe what I should do is in my solving, I should show you what will happen if you do assume h is a function of time. That would solve a more general problem. But then for this problem, we will assume ultimately that h is constant, so that dh dt is 0. But just for the sake of doing it, it's not the easiest way to do the problem, but just for the sake of illustrating it, let's assume at the start here, x and h are functions of t, which does mean v is a function of t as well. But you don't see any t's in that equation. It's okay. I mean, you could put t's in there if you wanted to. You could write it as v of t equals 1/3 x of t cubed times h of t. That probably would be better, to tell you the truth. If x and h both depended on time, it probably would be better to write the equation that way, to emphasize the dependence on time. It's just not traditional to do so. Why? Well, just a little extra writing. Mathematicians and scientists, when they're doing their math, are often feeling lazy in their writing. They want to be as efficient as possible. So they write as little as possible, which, yes, does lead to confusion. But we're trying to dispel the confusion here by confirming this is what's really going on. And not only do we assume these are functions of t, but we also assume they're nice functions, differentiable functions of t, so that I can differentiate both sides of this equation with respect to t. And I don't have to worry about lack of differentiability, for example. Yeah, differentiate both sides with respect to t. I will now use the equation without t's explicitly in there. I'm not writing the t's in there, but I'm imagining they're in there in my mind. I'm imagining it's this. What's the derivative of left-hand side with respect to t? It's not 0, because v depends on t. It's dv dt, or v prime of t if you used function notation. What about the right side? I need the product rule. Oops, there's a mistake, isn't there? This should be a 2. I need the product rule. I got the product of two functions, say 1/3 x squared and h. Left and right. Lefty right plus righty left. Left, 1/3 x squared, d right, dh dt, which will be 0 for our problem as stated. So this term is going to go away because h is not changing in our problem. But if we did allow h to change, if we allowed erosion to erode the height of the pyramid too, then dh dt would be something non-zero, some negative quantity. That's left d right plus right h d left. Okay, with the derivative of the left, I need the chain rule as well. Just like with implicit differentiation, I need to bring the 2 down and get 2/3 x to the first power, then times by the chain rule dx dt, and then times h. Simplify a tiny bit. There's not really much to do to simplify. 1/3 x squared dh dt. I'll just get rid of the first power there, and maybe I'll put the h next to the x. 2/3 xh dx dt. You want to do all your differentiation in these problems before you plug in any numbers. That's very important. It's a common mistake when people do these kinds of problems. They see these kinds of conditions up here and they say, oh, I guess I need to plug in h equals 120 and x is 150 right away. No, don't do that. Then you get a constant volume that wouldn't change over time, and that's wrong. It is changing. Differentiate first before you plug in any numbers. We've done that now. And yes, for our problem, the height's not changing, so that's 0. So this entire term goes away. dx dt, that's the negative 0.002. Now, the author doesn't, in the textbook, doesn't say whether this derivative is constant. is it always negative 0.002 or only at this moment in time when the height is 120 and the base is 150? They don't say it, but it wouldn't matter. It could either be a constant derivative for all time, or it could be just a derivative at this moment in time. And you're not saying what the moment in time is. That's okay. It's not a big deal. It's now, whatever now is. Now you plug in the other numbers, dv dt, evaluated at the condition where h is 120 and x is 150. I get 2/3 times 150 times 120 times negative 0.002. Two-thirds times 150 times 120. It's a big number, but then times negative 0.002, about negative 24. I guess exactly negative 24. Don't forget units. Units of volume per unit time. Distance units are in meters. Time units are in years. So it's negative 24 cubic meters per year. That's pretty astounding. If the length of the sides, x, is decreasing at a rate of 2 millimeters every year, which is, like that much, the volume decreases by 24 cubic meters per year. Whoa, how did that get so big? Well, it's because it's a big pyramid. That's why. Tiny changes in x lead to relatively large changes in the volume. Now, how big is 24 cubic meters? Well, take the cube root of 24. It's about close to 3. I'm, 2 meters tall or so. Imagine another half of me up here, and then imagine a cube that big. That's how much volume the pyramid is losing every year. Seems counterintuitive, but if I haven't made a mistake, it's correct. It's not just the side lengths changing, the diagonals are eroding too because x is decreasing if it truly remains a perfect pyramid. So that might help a little bit in terms of your intuition. The loss of volume is not just at the base, it's through the entire pyramid. Okay, so there's an example of a basic kind of related rates problem. But again, I could also have a non-zero value for dHdt. Some negative quantity could be here, and that would contribute to dv dt as well. Got time to maybe think about one more problem here? Maybe an easier problem. Well, how about a two-dimensional one like number 28? Okay, so we're just doing geometry ones here today. The area A of a square is increasing at 3 square centimeters per minute. How fast is the side length changing when the area is 576 square centimeters? These are called related rates problems because you are relating rates, relating derivatives. The equations that we got here in the last problem, the derivatives are rates and the equations relate them. That's why this is called the related rates. So we're imagining a square. In general, having side length x. Area equals x squared. We're told that the square has an area that's increasing. The square is getting bigger. Why would a square get bigger? Well, it depends on the situation, the application. I don't know. Maybe the square is a base of a pyramid that's not a pyramid in Egypt, but instead a pyramid of for a box and sand is in the box? Well, no, that wouldn't make sense either. I don't know. Use your imagination. The square is getting bigger. How fast is the side length changing when the square is 576 square centimeters? We're told the area is increasing at a rate of 3 square centimeters per minute. dA dt is 3 square centimeters per minute. That's a given. We want to find dx dt when A is 576 square centimeters. Again, everything depends on time, really. It'd be better to write this equation as A of t equals x of t squared. We're trying to solve for dx dt. You do not need to take the square root of both sides of this equation before you differentiate. You don't have to do that. You could just differentiate it as is. Take the equation, assume a and x depend on t, differentiate it with respect to t. The derivative of a with respect to t is dA dt. The derivative of x squared with respect to t, careful, not 0, not 2x, but 2x times dx dt. It's the chain rule, because x depends on t. Now just solve that for dx dt, because that's what we want to find. dx dt is 1 over 2x times dA dt. Plug in. Okay, we're going to need to plug in x to evaluate this based on A being 576 square centimeters. We do need to solve this equation for x by taking the square root. When A is that area, what is x? X will be the square root of 576. (24). The square is getting bigger. This is just a moment in time when I write those equations down. Just a snapshot of a moment in time. The square is getting bigger over time. At that moment in time, you can now plug the number in for x and plug in what dA dt is, 3. This simplifies to 1/16. What are the units? The units for the rate of change of x with respect to time, that would be centimeters per minute. So when the square is 576 square centimeters, 24 centimeters on a side, a square about yay big. Look at my hands here. It's increasing in area at 3 square centimeters per minute, so it's fairly slow. Yeah, that'd be slow enough to hardly be able to tell. X is increasing by 1/16 of a centimeter every minute. Yeah, that's less than a millimeter. This very slow growth of this square. Once again, don't plug your numbers in until the end. Take derivatives, assuming things depend on t. Right, first, solve for the unknown derivative you want, then plug the numbers in.